Okay, so let's see. So I want to do a quick recap of this neural net stuff we discussed, and then we will move forward to recurrent neural nets. So neural nets we discussed so far look something like this. They keep feeding stuff forward, okay? There is no loop, right? They are sometimes called feed-forward neural nets because of that. Okay, so what do? You got this computational graph, right? And then you have a loss function in mind. So this is your neural net. Theta is all the parameters involved. This is your data. You put it in, it spits out some guess, and you check it against your label, and you put a loss on top, right? And then last class before this spring break, I think, was it you, Adam? Someone was asking me about batch size and stuff. So what is batch size? It's this capital N right here. So your loss function is defined for every single data entry. And how many of them you put into your system, you get to decide. Okay. And there is no science established on batch size yet. Some number of years ago, Jan LeCun was tweeting, friends don't let friends use more than 32 batch size. But then people started using more and being successful. So it's still of a debate. But this is your batch size. And how does it affect what you end up doing? So, look at, so how do we train, right? So we are going to train through data. Very good. And we are going to try to minimize this loss function, right? And how are you going to minimize loss functions? Starting next lecture, we will start talking about that, optimization algorithms, right? Whenever you're training something, you pick an optimizer. Okay. And what those optimizers do, they usually take derivative of this stuff or use derivative of this stuff given by the computational graph. You take gradient of this. You don't want to take Hessian, but if you have to, sometimes you also take Hessian. And the gradient will be immediately determined. How does it look? By the data stuff you put in. Okay. So if you put a lot of data, then when you compute the gradient of your loss, you're somewhat confident that it's probably a good direction. Why do we care about gradient? All we want to do is we want to change these parameters. You start with some parameters, and then you keep iterating through data, and you keep changing the parameters. And when you think you're done, you freeze it. That's your neural net. Okay, that's it. So how do you update? You go in the direction of gradient or something of that sort. So all you're trying to do is like finding a good direction to tweak your parameters. Okay, so if your batch size is small, your gradient could be too much jiggling around. If it is large, probably gradient is good, but then you might end up having some other issues like exploiting, vanishing, whatnot. So you have to balance. Okay. And then we train through data using these optimizers. Then what do? We test, right? So that's always what you do. And then when you test, you get the test error or the loss on your test data, basically. Yeah. And then you start comparing like how was your training error versus how was your test error. If your training error was great, but then test error comes out super bad, that means you overfit it, okay? Likely. That means you fit so much to your data. Still, this is not fully scientific discussion, but there's a lot of empirical evidence suggesting overfitting is a thing, and then you have to care about it. So what are the tricks to care about overfitting? So first trick is regularization. What is regularization? This is your loss stuff, and this is your parameters. And at the very beginning of semester, we started talking by norms, if you remember. L1 norm, L2 norm, LP norm, whatnot. If you forgot, go back to those lectures. Just look at the pictures of those balls, you will remember more or less. And you put those norms on top of your parameters as a penalizer. What does this mean? So you put L1 or L2, or you could put other stuff too. Usually you would go with L1 and L2. That's the common practice, but you could do anything you like. And then what does this do? So if you put, say, L2 penalizer, when you're trying to optimize this objective function, it's called regularization because you're regularizing your loss function with this thing here. And this lambda is a number you get to pick. If you put lambda high, that means you're penalizing a lot. And if you're putting this low, It's getting closer and closer to just optimizing this, okay? And if you're trying to optimize over this, your model is not going to give you a huge parameter vector because you're penalizing by the norm of that parameter vector. Okay? But when you put L1 versus L2, L2 will only care about how big is that. L1, as we discussed, also cares about sparsity. Okay? L1 penalization would prefer getting lots of zero or close to zero entries in the places that it is not seemingly useful for your objective, and make the others, maybe one or something. So L1 would care about sparsity. L2 wouldn't care so much about sparsity. It would care your thing doesn't get too big. Okay, and we'll talk about this starting next lecture as well. So we'll start adding regularization to standard stuff we saw at the beginning. So at the very beginning of semester, we saw like classic algorithms, linear regression, logistic regression, that kind of stuff, right? And the easiest example to understand regularization is add those to linear regression and see what you get. Okay? Add those to logistics, see what you get. And all those additions has a name, okay, less or whatever, whatnot. You'll see, all right? You'll see more of these. That's one trick. Another trick is called dropout. So dropout was introduced by these people. I forgot the year, maybe 11, I don't know. We can Google and double check. And what is it? It's an extremely simple idea. They're saying if my model is overfitting, I'm kind of using a much more complex model than I'm supposed to, kind of intuitively. So they literally drop out some neurons in a probabilistic way. Okay, you get to pick the probability of dropping out. So it's like present with probability p, not present with probability 1 minus 2. You get to pick that p. This is implemented in all the packages you might be using. The default p is usually half. If you want to make it sparser, what you do, you make the probability of being present less. You're going to keep killing more neurons, all right? So there's a whole bunch of experiments in this paper. This technique also seemingly works out. And they have some funny biological intuition that I always find amusing. If you read the paper, you'll see at the beginning. I don't see anything that this has to do with biology, but it's fine. All right. And then there's another technique called Bayesian neural nets, which we may touch upon sometime the rest of the semester. It's not a big deal, but it's something good to be aware of. There is such a thing that exists. If you need it one day, you might go consult. I'll touch base at some point during the semester. And there's another technique called beam search. You'll probably see it today. It came out when people were training recurrent neural nets. This is, again, just to avoid overfitting. These are like standard techniques to deal with overfitting. Of course, you're allowed to be creative and design your own techniques. And okay, what's next? What else? There is the other issue of vanishing and exploiting gradients. Do you guys know this game called Exploiting Kittens? No? No. Okay, no one knows. I don't think anybody has a young kid here. Exploiting Kittens. Yeah, you know, as every time I'm trying to explain exploiting gradients, that's what I remember. It's kind of a goofy game, but it's kind of fun. Okay. All right, so what are the techniques? We got gradient clipping, which means you literally clip the gradient if it is bigger than a certain threshold. Then we have this normalization tricks. So a common one is called batch norm. What does it mean? You take all your batch, you normalize. Another one called layer norm. In this case, your batch size may be not so big. So normalizing through the batch is not a good idea. Think about this capital N being rather small. In that case, you might just average over your single data point, let's say one image. And then there is this group norm and instance norm. This is all normalization tricks. And normalization is kind of standard. However, in spring break, Jan LeCun released a paper with his group. They do a clever, like adaptive 10H function instead of normalization. And it seems to be doing fine too. So I'm sure this is going to be an ongoing debate, okay? So all this stuff, as I said, are mostly intuitive engineering, good stuff, but not scientific. So 10 years from now, I don't know if we would be talking about normalization or not. If you live, you will see it all together. Okay. All right. And then there is also this residual connection. What was residual? It was this res net that we talked about in convolutional neural nets. Literally what you do, you take your data, you put it in your stuff, and you attach a copy of your data next to the output of your neural net layer. And this allows the propagation, back propagation to keep flowing. That's again a trick. And then there's also this initialization tricks. Since the optimization we are trying to do is not like a nice convex optimization, the initial weights you put when you start the training matters. If you put wrong initialization, you might end up getting trapped in a local minima, which is not globally minimum. You want to minimize your loss function as much as you can. Okay. So initialization matters because the optimization you're trying to do is not an easy one, but we are still trying to use easy algorithms. And what else? We also discussed this thing called bias variance trade-off, generalization gap, batch size versus learning rate, etc. So this, some stuff we discussed along the way. So this was just a recap of neural net stuff on a high level. I hope it was useful. This was motivated by the questions you guys asked. Any questions about this before I start recurrent neural nets? Recurrent neural nets means neural nets with loops. Yeah, go for it. You can see that way too, keep putting symbol and sum up. But then the point is you update the weights after you put all your batch. The way you imagine, if you like it that way, keep it that way. That doesn't change anything. You can keep thinking like one by one. The point is you sum up the loss, then you figure out how to update after your batch is went through. Yeah, go ahead. Yeah. Yeah. Exactly. 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 Yeah, that's why it's not terribly cheap to do. Yeah, more or less. I mean, like, depends on how you look at it. Let's say it's a very good question. So let's say you passed in a small batch or just even one data set. In computer science, what's the name of algorithms that sees only one data one by one? Online algorithms, right? That's streaming model. You don't save the data, you keep getting information and you keep updating along the way. It's not only computer science, also in electrical engineering, there is this old thing called Kalman filter, which is an online algorithm. Of course, they didn't know the name in 60s, they didn't call it online algorithm. So yes, that's the extreme. You can put only even one data, right? So what could be the issue? Let's say I put only one or two data, then I computed my loss, then I computed the gradient. So gradient essentially reflects what you learned from just small data. So that may be very skewed. If your data is coming from a particular part in your data space. Larger sample size means, hopefully the gradient you figured out is a reasonable one, not a crazy one. Then it will be a lot of time before you do any update. You don't want to wait until updating too long. Very good question. Yeah. You need to strike some sort of a balance because you want to keep updating at the same time. You don't want your updates to be totally not so intelligent, somewhere in between. Yeah, very good. Exactly. Batch size, learning rate. There's a whole bunch of hyperparameters you can tune. There's more and more packages, which does a lot of experiments for you these days. I'm not fluent in all of them. 2 weeks ago, we were playing with one, which also allows you to hyperparameter tune through the architecture as well, not only the weights. You make the sizes of certain things also a hyperparameter. the package keeps doing a whole bunch of experiments for you. Just let the thing run a day or two, then it gives you all the. Anyways, so basically all of them are empirical. For example, this lambda in the regularization, the standard technique is just basically cross-validation. You keep trying and trying to see what is the best lambda. All right, so this is some general stuff just to warm you up with neural nets. Now let's start talking about recurrent neural nets. I don't know if I'll be able to finish everything I need to say about this stuff. It's a lot of ideas. Let's see what we can do. I'll maybe end up doing a few more in the next lecture, but I don't want to make it linger. I have to also cut it and go to optimization. All right, so about recurrent neural nets, what we need to go through. First, what the heck is a recurrent neural net? What's a recurrent neuron? That's the starting point. And then recurrent layers. Then there's this names, vector to sequence, sequence to vector, sequence to sequence, whatever that is, I'll tell you. And then how would you do backprop in neural nets? Because what we talked so far is always about feed forward. Neural nets also has a loop going back. Backprop, as we talked, doesn't fit directly. So we have to think about that too. All right. And then these fancy things that people invented, LTSM, long-term short memory, GRU, gated recurrent unit. So this we have to talk about. So what are those? So people, started inventing these neural nets and training them. And then there comes a problem, which is the following. So the neurons are, say, firing, and what you want to do in recurrent neural nets is this. Let's say I'm making a sentence, right? I like croissant and I speak question mark, then maybe French. Right? So, and then the guess of the neural net will be based off of what it has seen so far. It's almost like predicting a time series. You have seen so far what it is doing, what's next, okay? Then like very local relationships, seems like neurons are figuring them out. I like to play, then maybe neuron is figuring out, it needs to be a game, basketball, soccer, but that's nice, that's local. And then since you keep stacking up the stuff, somehow it also starts figuring out a very global structure, like grammar, for example. But then there's things in between. Let's say I need to understand the word based off of like 20 words before. There is where the problem started occurring. So you need some sort of memory to remember the context and then figure out the next based off of what you have seen so far. And you don't want to memorize everything. This will be just memorization. It wouldn't be learning. So there is an interesting thing to figure out there, like how do we emulate memory in our machine learning architectures? Okay. So this LTSM, apparently in the 90s, some Germans figured out the straightforward way of recurrent neural nets is not going to work, and they had papers about it. No one was aware. One of them is a master's thesis in German in München. Okay, and then there's an English version, blah, blah, blah. And then after people start seeing these issues, these guys write another paper saying, we told you so, this is how you fix it. This is apparently what they invented back in the day. And then people start using it. And then it's quite intricate. We will hopefully see today. I like it very much, but it looks very much like German engineering. Then people started simplifying it. This GRU is one of those. There's variants of this LTSM. And the simple ones empirically seems to be doing just fine. And then after all this comes the idea called attention. And then after attention, started popping out here and there, people were seemingly convinced that attention is like the next big thing after this LTSM. Then these guys, in the paper called Transformers, what they do is the following. They say, forget about all the recurrent neural nets you have been doing. It's sequence by sequence, impossible to compute in parallel, pretty hard to do. We will just do something else. We will forget about that recurrence. We will do just attention. And the title of the paper is literally attention is all you need. We'll talk about it a little bit. And I don't think you'll have any time after this, but if we still are alive and have time, I can talk about state space models, but I don't expect, okay? This state space models, I am more excited about them than transformers. They're more recent. You know, nowadays everything became transformers. It's kind of, I don't know. I don't like to see transformers all the time. You want to see some new idea, right? So this is a new idea. Anyway, all right, let's get going. So this is a recurrent neuron. So what does it do? You put the input here. I was just putting some, stuff. This is a summation like matrix multiplication or something. And maybe this is like ReLU, rectified linear unit. Then it does an output, but it also puts it back inside. That's a one single recurrent neuron, okay? And then what's gonna happen is like, as you keep doing this over the time, it's gonna keep feeding itself and outputting at the same time. Okay? And the reason for that is you're trying to emulate the dependency of a current data on the ones that you have seen in the last 10 steps. Think about trying to complete a sentence, translate a sentence from one language to another. Guessing what's going to be the electricity consumption in San Antonio tomorrow based on what it was in the last year, blah, blah, blah. All kinds of time series. That's why they are doing this recurrent neural net. Okay? But there is a small trick which makes it look like the feed-forward neural nets we have seen so far. It's called unrolling through the time. You make copy of the same neuron next to each other based on the time you allow, and then you just back propagate through the time. Okay. That's the dirty trick that makes this thing work. So you don't need to invent anything new. For every time step, you just need a copy of your neuron. So it becomes, of course, more expensive, but you can still do your back prop as you were used to. Okay, so that's going to be one neuron. But of course, you want to put them next to each other and make like layers of them. This is my hand drawing of how a layer would look like. You put all these neurons together. When it spits out something, it puts it back to all of them. Okay? Because it has to do the recurrent loop, right? So that's how a layer of recurrent neurons will look like. And if you unroll it through the time, you'll be making a copy of that layer and then back propagating through the time. Yes. There is a one input. Very good question. So I was going to do it in the next page. So the reason probably Adam was asking is like when you see pictures of these recurrent neural neurons, they will not only be an input and an output. Usually there will be one more thing. Okay. So in this simple picture, that one more thing is the same thing as the output. But when you see something not in this lecture, but just like more commonly used, you would also see something called a hidden state. Usually recurrent neural neurons creates an output and a hidden state, and it gets an input in. That's why you see two things coming out. Okay. In this simple example, hidden state and the output is the same thing. That's why you don't see two. And hidden state is created because of the following reason. So input is ordered by time, first input, second input, and kind of the outputs are ordered the same way. They come out as input come in. Hidden states doesn't have to respect that time order. So it gives you more flexibility. Okay. Very like yeah, that is true. That is true. Could you say it again? I couldn't hear. I mean, literally, so this is literally what the thing is implementing. But you have a very good question, like, can the neuron change over the time? So when we go to this LTSM, it's not going to be a single neuron that changes over the time. They created like a small circuit of neurons that changes over the time and tries to learn what to remember, what to forget. Okay, for the moment, same neuron, just copies of it. Yeah. All right. So, yeah, as I said, in the simple form I showed you, the output is the same thing as the hidden state or the feedback. And in general, if you look at your textbook, you would see an expression that looks like this. Don't be scared, okay? It's easy, I'll explain. So your input, your previous output, your previous hidden state gives you the next hidden state and the next output, okay? Basically, that's what it is. First, next hidden state, then based off of that, next output. Okay, that's basically the model. Don't forget about all this, fancy looking math. What it is saying is like what you're producing now as a hidden state is based on all the hidden states and the outputs and the inputs before. And then when you got that hidden state, you also produce your next output. And the book gives some like more concrete stuff. It says, for example, when I produce an hidden state, I might go do the softmax in the logistic regression we were doing, or maybe I do some Gaussian, it's talking about how do I go from hidden state to output. In the simple one I showed you, this is literally the same thing, okay? In previous page, okay? And you get to design this yourself too, of course. That's the general model. And when you put also the hidden state in the picture, this is how it starts looking like. You get the input, produce an hidden state, then an output, hidden state comes in here, the output also comes in here. You see how it goes, right? Now let's get to this sec, vec, whatever vocabulary. What does that mean? You think about the input data as a vector for the moment. This X is a vector. And you're producing a variable length output. So you decided to produce 3 of them. And you don't even have to look at all the 3 of them. You can just look at the last one, last 2. You get to decide how many you're outputting. That's why it's called vector to sequence. Vector has a fixed length, that's the input. Sequence, you get to decide, okay? This version is called vec to sec. And then what are the other versions of the same idea? You could do sequence to vector. That's an option. So you don't fix the input size, but you fix the output size. And you would, let's see, for example, why would you do that? Let me zoom out. Yeah, so not like for example, you might be trying to classify stuff. Then the vector output will be class 1, class 2, blah, 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 probabilities of those classes. Or you might be doing what's called sentiment analysis. What do people think about a certain product or a political opinion or whatever else? Okay. And in that case, it looks like the picture you see right there. This is sec vec, okay, sec to vec. Okay, this is what that. And then the thing I usually see more, probably because of what I read, is like sec to sec. And how does sec to sec work? Let's say you're translating from English to German. You take a sequence, all the words, okay? And then they got translated to a vector inside your model, and that vector gets translated back to German, okay? That's sometimes called encoder-decoder structure. You go from sequence to a vector, that is your encoder, and your decoder takes that vector, turns it into another sequence. This is how usually sequence to sequence stuff goes. Any questions anywhere? Okay. And there is one more catch. Hidden states does not need to be ordered by time, in the sense that, they're not like sequential as input data or the output. You can let them be more free if you want to. So far, we did not let them be free. We make them sequential, but you don't have to. So here in this variation, what people do, they let the hidden states be bidirectional. And it's called the bidirectional RNN. Okay? It keeps feeding back and forth, not only one way. If you like, you can do that. Okay. So far, how these neural nets look, that's what we are discussing so far. Any questions? Jordan, question? No, okay. Yeah, so the picture here you see is this encoder-decoder architecture. The C in the middle is the vector. It goes from sequence to vector, vector to sequence. Okay, let's keep going. Now, back propagation through time. As we talked, this is basically unrolling your network through the time and doing your usual back prop. You're attaching a copy of the thing on top of each other. That's how you should think about it. Okay? And that's why it's called back propagation through time. And then in Matthew way, from our textbook, how would it look? Let's say this is your hidden state, your input, previous hidden state, and the book, to simplify it, doesn't even use the output. And then here is your guess, and then is a loss function, and this is your loss function at the time t. Okay, I hope this backprop through time is intuitive. Any questions about this? This is the usual backprop as we discussed after unrolling. Because if you don't unroll, that recurrent structure makes it very tricky to think about. Okay, very good. Now let me see how much I want to tell you about this part of the textbook. Let me see. So what do we need here? So you have weights going from your input to hidden, hidden to hidden, output to hidden. And then the book sits down and works out how those derivatives comes about. And you don't have to, of course, know this or memorize this. It's just like, it's fairly straightforward. That's the punchline. You just do your standard gradients, they come out, and you start your backprop, train through it. But there is some computation, okay? It is, you could write down these formulas yourself, it's straightforward, or ask your computer to write them down for you, right? However, even though they're straightforward, you see this requires a lot of compute, okay? So recurrent neural nets are usually not so cheap to train because everything in the structure is expensive, all right? Now, when you look at this formula and think about propagating this through the time, and if that time is long, it's going to get more and more evolved computation. So what people do, they start playing tricks to make it faster. One trick is truncate, which means instead of going through all the time, make your current situation be dependent on certain number of steps before your current situation. Don't go through all the time. Go through last 10, last 100, last 1,000, whatever you decided, okay? That's truncation. Truncation is a standard naive trick all over computer science, math, and it usually doesn't work, okay? So, but it's the first thing you would try, right? So that, you know, we do this all the time in many things, but sometimes it does work. You know, let's say we have this optimization algorithms. We'll talk about gradient descent, Newton, whatever. They all are based off of truncation. You take a function, do the Taylor expansion. Taylor expansion would be huge. Cut it at the first or second, go from there. That's basically what you're doing. Okay? But as soon as you see truncation, you need to be careful. And in this case, after experimentation, people realize they need to invent new tricks. And one of them is called beam search. Let me motivate it before I tell you what that is. Okay, so this is a neural net that was doing English to French translation. And they try to use a greedy approach. So what do? You output next thing as the one that is the most probable according to your current computation. So you're in a certain state, you look at what is the most probable next word, you spit it out, and then you keep doing it, okay? So what could go wrong with this? This looks very reasonable. Like I put in stuff, and when I'm putting it out, I keep picking the best current guess. You know, standard greedy algorithm, right? That's, we have a whole bunch of psychology. What could go wrong? Well, what could go wrong is like, you're at the end not trying to just figure out what's the most probable next word. You're literally trying to translate a sentence or a paragraph. You need a globally optimal path, not just locally the best thing. Okay, so then this can give you a whole bunch of issues because of that. Still, there's a lot of success based off of this. Okay, but the main issue is like local greedy does not necessarily give you the global translation you are trying to do. Then the update to this idea is this thing called beam search. So when I'm picking the best guess, I'm basically picking one thing at every single step. I'm being very greedy. Now, we want to allow the model to explore a little bit and try to figure out that recurrent structure, the global way the things work out. So what they do, they say, okay, I decide on a K, which is bigger than 1. 1 is the greedy. 5, 10, 100, whatever it is. At every step, look at the top 10, top 100, top 1,000, whatever you allowed it. This is much smaller than the entire vocabulary. Then you keep going that way. That's called, you optimize over this tree, basically. That's called beam search, okay? Any questions about this one? So you will see all this stuff used when we see actual architectures. That's why I'm one by one introducing them to you, all right? Okay. Let's go to the next one. And then the other trick is tokenization. What is tokenization? So if you played with LLMs at all, this is the thing that gets it running. Actually, let me see if I can open a fun app about this. And if I manage, we can see tokenization. Click tokenizer. Yeah, there you go. So for example, you pick a model from here, say, and then you start writing a sentence. I don't like to teach at 7 p.m. Okay. And then you see, what is this tokenizer doing? It's trying to split the input into literal tokens that are encoded by these numbers you're seeing right here. This is what the model is saying. It's not seeing what you're writing. Okay. And how do you tokenize? A very important question. Maybe first question, why would you tokenize? For efficiency. Otherwise, you could go literally character by character, one letter after another, but it's going to be very hard to train. So, and this, I don't know which model was this I picked. This is the tokenizer that model is using. And this is how that model is seeing what I wrote down. So the two things in all these large language models is very crucial, but always goes under the hood: tokenization and embedding. So one thing is you tokenize. Second thing is you embed all the stuff to huge vectors. Okay? And then when you're looking, if two things are similar, you look at those vectors. So vector embeddings and tokenization, critical, but almost never gets talked about when you read algorithms. Okay, I hope now tokenization is more concrete after you saw how it looks. And of course, there is normalization tricks. Okay, so things can explode instead of going like a rocket. Why? Because imagine you're doing this recurrent neural net, you're putting copies after another, and let's say, just pick a matrix there, all right? And you keep multiplying those matrices. Let's say Jacobian matrices that is involved when I'm doing backprop. And if that matrix is enlarging the input vector a little bit, let's say we talked about the singular values. What was it? The biggest one is how much it enlarges. At most, the smallest one, what is the smallest enlargement this is doing? And suppose the smallest enlargement this matrix is doing bigger than 1. For the sake of discussion, even say 2. When you go 10 steps, it's going to be bigger than 2 to the 10. And you're going to go much more than 10 steps. So things can explode very easily in recurrent neural nets. So you have to be careful with how you normalize it. And that's about it. So now the more interesting part of the story is about the memory. Again, probably you guys don't know this cartoon. Maybe for parents only. So this is like Finding Nemo. And then that's, what was it, Dory? I forget Dory. That thing right there forgets everything. And in the cartoon, if you watch, it starts a sentence, and in the middle, it forgets what it was saying, so it cannot complete the sentence. And if you don't put memory in your recurrent neural nets, that's how they start behaving. Okay, they forget, so they don't know how to complete. So that's why people invented this thing called long-term short memory. And I'm using illustrations created by somebody called Chris Olach. I think I will put the links to his very nice writing about this. So this is how LTSM unit looks like, and we'll go through it step by step. You're stacking these LTSM units next to each other instead of just stacking a neuron. Okay. And that goes back to Owen's question. This thing can change along the way. Idea. This unit is designed to learn what to remember, what to forget. Okay. How does that go? So, so this stuff is your standard neural net things like sigmoid functions, some sort of activation, or you can put like a few layers of multi-layer perceptron. So this means some standard neural net trick. This means some pointwise operation, add two things, multiply two things. And then I think you see the rest. There's concatenation and copying. And okay, let's start going. So this thing that goes through left and right, this is called cell state in this LTSM language. Okay. And the first one here is called, so this thing is going to get a lot of information inside. And using those, it's going to spit out something. And then there will be also a hidden state spit out. So what are those operations? We will go one by one. Okay. So the thing on the top going left to right is called cell state. And the first thing there is the thing on the very left. This is called forget gate. This tries to figure out from the data what to forget. Okay? So you get your previous hidden state, your input data. You're trying to figure out the correct weight, like correct kernel. And there's some bias so that what to forget will be known. And what to forget means this neuron did not fire. This is an activation function. You compute this number. You put it inside your activation function. You can use any activation function you like. Probably they use 10H, I would guess. And then if it fires, you're remembering. If it is firing strongly, you're remembering more. If it is close to zero, the output, you're trying to forget. It goes between 1 and 0. That's the forget gate. Now, let's see the rest of the gates. And the rest of the stuff is kind of trying to see what to remember in a way. So you put your previous state inside here. And then also inside your, I think this should be probably sigmoid. This is 10H. I guess the math is kind of clear enough. So this one right here is your sigmoid on top of this. And then this one right here is your 10H. Then you multiply them. This is your multiplication operation. You put it here. And you get your forget. And forget's multiplied with the previous cell. You're trying to decide how much of it should be forgotten. And this is what to remember. You add them, you spit out as the next cell. Okay. And then there's also this intricate thing to figure out what should be the next hidden state. Well, not too intricate. You can put some sigmoid, put 10H, and spit it out. This thing is, as you see, has a lot of steps in it. And you try to learn all these weights involved in all parts of it, all this stuff right here, through data. So it was working, but it, it's not so cheap to train. So people tried kind of streamlining this design. And one most common one is this thing called gate recurring unit. But it's not the only one. So what they do, if you look at this picture versus the one on top, on the middle here, literally they are combining two gates into one, putting less weights and experimenting. Instead of remember, one more, let's try to make two of them one. It's literally full experimentation. And experiments suggest this thing is seemingly working as good as the LTSM when you're doing large scale training. So this and other variants more or less replaced LTSM afterwards a little while. But there's so many architectures. In some experimentations, there's like thousands of architectures people go through and try which one is doing what on whatever translation, goal they were working on. It's hard to, at least for me, it's hard to tell you like a more principled way to think about this architecture is better than the other. But it may be because I'm not a terrible expert on this, or it may be because the state of the art is not there yet. Okay. So far, so good. Now, after this delicate and kind of working out machinery being expensive, people started thinking about how could we come up with different ways which is more efficient. So one particular problem is this copying stuff on top of each other and being very sequential. You just have to wait until the sequence comes out. But in practice, we would like to compute in parallel. That's how we speed up things. But just by design, you're not able to do that. Okay. So that's a particular issue about all these recurring designs. The next thing that comes out is called attention, which does not need to wait until everything is done. But let me motivate it slowly. So you guys probably have seen dictionary data structure somewhere. How does it go? You have a key, you have a value. When you call the key, it spits out the value, right? I don't know which language you're using. In Python, it's literally dictionary. Right? Okay. And it's like a hash function or something, right? And can we make this a bit softened? What do I mean by that? Let's say somebody gives me a query, and I'm going to check it against the key. If it matches, I'm going to spit out the value. If not, I'll say, sorry, that's the dictionary data structure. What if I don't be this strict and I just say, check that query against all the keys I have, which ones look similar? Give a mixture of those as an output. Yeah, kind of similar to this convolutional neural net idea. We were like pooling over a patch, right? So here it's going to pool over certain values that seems to be matching the query key a little bit. Okay, that's the softening the dictionary data structure idea. And how does it look? It looks like this. These are my values. This is the query from the user. These are my keys. This is a score function that's scoring how similar is the query to the key somehow. And if it is 0, that means don't put this value in. If it is a relatively big number, you get that value in. And you mix them up, you're literally averaging over values, and you spit it out. That's the attention. Why did people call this attention? Well, think about like even using this for image stuff. This is literally trying to figure out what part of the image is relevant. That's why they call it attention. Where is this thing trying to give the attention? Okay. And this is actually a very old idea. So this attention existed in statistics and stuff very long time. But then bringing it back to machine learning was maybe a clever idea at the time. So, and you want to make this weights usually like a positive small number, and you want usually them to sum up to 1, because you can think about it as assigning probabilities to values essentially. If it is 1, this is the value, right? If it is like half of, maybe 2 of them combined, something like that. So to do that, usually people will come up with some value scoring function and do this X soft max type trick. This small detail. Okay, at the end, you want these stuff to be positive numbers between 0 and 1, and you want the sum of those stuff to be 1, which represents the probability of all the values in your dictionary. Okay. And so these are like all the attention stuff. Who knows when they were invented? In this 2017 Transformers paper, they did not want to use the classic ones, which are a little expensive to compute. They looked at what is the cheapest possible attention we could design, which would work still okay. Okay. The cheapest thing you could do, make your query a vector, key a vector, take inner product, see how big is that inner product. That's the cheapest thing you could do. Right. And that's what they do. They literally take the inner product, and then they realize this thing can become a very large number. Then they normalize by the square root of the dimension of that vector. Okay. So you, as I said, you tokenize, then you vectorize, and then you look at that vector, it's got a dimension. And that's what you're normalizing with so that it doesn't explode. So that's the attention mechanism used in that paper. And okay, so this is literally the code that can write up the attention mechanism. So how they do, they say, we don't want to go one by one. Put all the keys as a matrix, put all the queries as a matrix, do that softmax cleverly, and then multiply it all with the matrix that represents all the values. Okay, it's just a clever trick to do it. This is how the architecture looks like. You do Q and K matrix multiplication, scaling. Mask, I'll talk about it in a sec. We don't need mask just yet. And then another matrix multiplication with this V. And it's literally the code that can give you that. It's not complicated. That's what I'm trying to say. Okay. All right. But then when you want to use this attention for like trying to translate stuff, that was their purpose in this paper. It doesn't care about global structure at all. It doesn't care about the order of words. You know, you're losing so much resolution, essentially. You're zooming out too much. Then what they do, they stack up attention layers next to each other to go against it. It's called multi-head attention. Basically, the attention we have seen, you put a whole bunch of copies of it. So every attention layer will be looking at a different aspect of the input, hopefully. Then you'll concatenate and combine them. This way, hopefully, you will see different parts of the input data that was relevant. So more precisely, what do? You get a huge input vector. This linear stuff you see in the picture, these are taking projections of that big vector. You're projecting on different angles, basically. And then after that, you put attentions on top of different projections, and you concatenate them. And there's a lot of experimentation, seemingly nicely done around this paper. You can almost interpret what's going on. It's very interesting. So you can almost see the attention is going on different important directions of the input data after a lot of experimentation. So because you did this and you still don't know if different attention heads are learning a different thing or they're just doing the same thing more than once you need to. Experimentation seems to suggest it's actually working out as desired. Right? So different attention layers are looking at different parts, and you end up concatenating them. This is the multi-head attention. Okay. Still, we did not care about this sequence of stuff yet. We will get there. So this is the Transformers architecture that took over the world. So this is how it looks. This is your input. I'll explain to you what is this positional encoding in a sec. This is your encoder. Let's go step by step. Input comes in. Forget about positional for a sec. I'll explain it. It goes through this multi-head attention. Then you got this normalization layer. And as you see, this arrow on the left means residual connection. You put a copy. After every 2, you put a copy. And then after that, they put like a standard linear dense layer, multi-layer perceptron, another normalization, feed it into the decoder. Now, when I first saw this, I remembered this looked weird because here there was 2, here there's 3. Okay. And I didn't understand why decoder and encoder are different. The answer is very simple. You know, after I understand, I said, Dumbo, why did you not get it in the first sight? Because you're trying to translate. That's what they're trying to do. Here comes in English. Here you should put in German, then match, right? This is what's going on. Okay? So here comes in the output embedding, the German stuff. It goes through this attention layer. Then here you're trying to match it with your English input, essentially. That's why the decoder looks one more step longer. Okay? All right. Let's see what else needs to be explained here. I think the only thing missing so far is positional encoding. And in the training, they use all the tricks I showed you. Dropout, beam search. You know, the reason I showed you, they're all implemented. Okay? So in the architecture, you don't see them, that they're in the implementation. Okay. So this is how your output vocabulary is represented. Yeah, so suppose you're translating from English to German. You tokenize German vocabulary and you vectorize them. Embedding means they're embedded somewhere. English, German, and you're trying to match them output to translation out. Exactly. Mm-hmm. And it's always auto-regressive, which means it's trying to figure out the next token all the time. Okay. So yeah, go ahead. Outputs. So very good question. So it's like you need to make sure the current output you're spitting out only depends on the ones before. We'll see a little bit more of that. Give me a sec. Okay, very good question. Okay, so what did I not explain yet? I did not explain this, or masking will come out soon, and positional encoding. So far what they have done, they said, I don't want any recurrence at all. I'm going with attention. And then they put attention together. They make this multi-attention head. And then they do this encoder-decoder structure. But then, of course, how are you going to make sure the dependency of the word now on the ones that is only before, not after, is encoded in your system? Without this positional encoding, there is nothing like that. Attention does not care about the order. It could mix up stuff, okay? So they invent this positional encoding idea. So, okay. Let me go positional encoding, then I'll tell you the masking. So what is positional embedding or encoding? Your data had some dimension D. Now we are going to put next to it another vector of the same dimension, which will somehow encode the order of the token coming in. That's the goal. How am I going to create it? You can do a whole bunch of creative ways. In the paper, they experiment learning positional encoding versus hard coding it. They seem to be performing the same, so you don't need to use your compute for learning. They just hard code it. What is the hard coding? Every coordinate of this gigantic vector will be a sine curve. Okay, it's kind of a crazy idea. So this is literally how it goes. Position the vector corresponding to a certain position. This coordinate of that vector will be this, and this coordinate of that vector will be that. And you will have a whole bunch of those coordinates, as much as the dimension of your data, because they're going to add this positional encoding next to the data right up. They want to make it the same dimension, so you add easily. Okay. Sine doesn't have to be the case. You can do a whole bunch of other creative works. But I think sine is a very nice idea here, because you can literally distinguish every vector from one another this way. And it's very easy to code. Just works out. So this is the positional embedding idea. They don't like hard code the order of input, but they give that information to the model this way. Almost ordered. Okay. Okay. Now the masking part. Now, in the output, I need to make sure the output, say in the 10th word, only depends on the ones before, not after. And the way to do it is they mask. What does this mean? The output 0 does not depend on anything before. It's just itself. Output 1 only depends on 0 and 1. This is the masked part. For masking, what they do in the soft mask, softmax, I'm sorry, they put that weight as infinite, negative infinity, so it kills out. They're masking by force. Yeah. And you shift one right so that, if you're trying to put out like fourth word, it only depends on the third. So that's the entire transformer architecture. And these are the experimentations they got out of it back in the day. So this is, I think, a 2017 paper. This is a specific error measure for translation people. You don't need to worry about what that is. Okay. And they compare it to state of the art. So they beat them in the error, but in the training, they do a little more. Of course, in that time, this gigantic models wasn't a thing. This was trained about like 4 days only, this transformers paper. Not like you train it a year, consume as much electricity as San Antonio consumes to train a billion parameter model. It was like more, a little more modest. And one thing I forgot to say, in the initial transformers architecture, they stack up 6 of those layers on top in the encoder. So everything has like 2 sublayers and 6 of them on top. And I think in the decoder, they also put 6 or 8. I have to check. Yeah, again, 6. So it's not necessarily a terribly deep network. Okay, still there's a lot of weights in it. Don't get me wrong. There's so much connections. You still learn a lot of parameters, but it's not as like the models we have these days, like, I don't know, trillion parameters. It's like 6 of those things stacked up on the left and on the right. That's literally the transformers architecture. Yeah. All right. Then what happens is, like, people realize this is not only good for translation, it's also good for many other purposes. And they start experimenting. When was that ChatGPT moment? 2021 or 20? I forgot now. 22. So 5 years after this paper comes the ChatGPT moment, which is based off of this architecture. So apparently this guy, Ilya Sutskever, had the insight that this thing is going to be very successful. And just like they did in the image competition, they won in 2012, they start stacking up this on top of each other, get deeper and deeper and deeper. And eventually, when it was released, we all knew about it. That's what it's based off of. And after this, now transformers is everywhere. Now there's this vision transformer, for example, instead of convolutional neural net, people use that architecture. It's so dominant that it is kind of annoying at this point. That's about it. Now, amazingly, I still have time. That means I went very quick today. Any questions so far? Mm-hmm. Yeah. Right. Yeah, that is true. But I'm not sure how it works out. Only thing I remember is from the experimentation, they see this multi-head attention is starting to figure out the semantics of the language. It starts to pay attention to semantically related words to each other. That's all I remember from looking at experimentation. That's a very good question. I don't remember fully. They do also more masking afterwards. So they also say, okay, I got like a sentence with 10 words. Let me mask, say, the third and the fifth and the eighth. Ask the model to figure those out, like fill in the blanks type question. That also helps improve performance a lot. Now, masking more or less is a standard technique after this success. But yeah, that's a very good question. I am not sure. Yes, right. Yeah. Yeah. For example, this is English to German, right? Yeah, exactly. So, in this example, German is literally almost the opposite of English in terms of grammar. The way it goes is like totally the opposite. It's a very legit question. I don't know the answer fully. All right. Now, in the last maybe 8 minutes or so, let me talk just a bit about the state space models. So this is a more recent idea. Now maybe still couple years old at this point. So this is like, why was the reason that people wanted to create this attention is because training recurrent neural nets was expensive and you're not able to parallelize the training. That was the main idea. So don't get this wrong. Of course, transformers is still expensive to train. It's not cheap. It's just that you're able to parallelize a little bit. So this state space models is trying to create something in between, like some sort of architecture that will look like a recurrent neural net from one angle, convolutional from another angle, whatever that means. Okay, that's the main intuition. And another intuition behind this is like this model is trying to imitate a usual physical dynamical system. Let's say a particle is moving here, changing its location. That's called state space in mechanics. And the easiest one, if you have seen any control theory, if there's an electrical engineer, this would look very familiar. That's a control circuit. Okay, so the easiest dynamics is the linear dynamics. What does that mean? This is my current state. And this is the control I apply. This is the action I take to change it. Okay, and then what is my next state? How much change happens? It's a linear function of my current place and my control action. Of course, not everything is this simple. A lot of things are very nonlinear. You know, let's say you're trying to treat a patient, you're a doctor, your control is giving the medication. Of course, the output is not linear. It's a very complicated thing. This is the simplest model you could create, and it models a lot of physical things, actually. Okay, and then this you could think about like the output. Okay, now this I think this guy, this was one of the early papers. Eventually, this person became like the state space person, Albert Gu. So if you Google, probably you will see one of his talks. After, they wrote a whole bunch of papers on this. And after that, I think he emerged as like the person doing these models. And there's a new company based off of these models. I forgot the name. Of course, this Albert Gu is either co-founder or, blah, blah, blah. Okay. Now, what is it? What is it trying to do? So it's going to try to do two things from two angles. One angle, it will look like a convolutional neural net. And from the other angle, it will start looking like a recurrent neural net where this location depends on everything else before. Let's see how much I could show you in a couple of minutes. Maybe before I tell you anything, so let me tell you two things. There is a wonderful exposition on this. I don't think I'll have time to tell you a lot of good stuff about this. I'll put the exposition on Canvas. If you're interested, read, and I'm happy to discuss anytime. Okay, there's a wonderful exposition that goes through this paper, writes the code next to it, very clear. There's a good chunk of math involved in this paper. You can either skip that part, or if you want, get into it. I'm happy to discuss. Okay, very good. So why does a lot of math is involved? So before we go on, as you see, this is not the first state space model. This is a little bit of improved version and a fast version. And there's this long range arena benchmark for recurrent neural net people. And in that benchmark, this state space model, as you see, almost beats up everyone else. Yeah. So it's quite promising, but it is still not the dominant thing. Transformers is still the dominant one. Okay. So let me see. Okay, very good. Say it again. Yeah, Mamba is based off of this idea. That is true. So Mamba is a state space model. That's right. Very good. And now they wrote a paper a few years ago in DeepMind called Resurrecting Recurrent Neural Nets after Transformers killed them. They are trying to use this type of idea to resurrect them back. It also seems promising. There's a lot of research going on. Let me try to see what I can tell you quickly. All right, very good. So for us, the control is literally the input that you're trying to match. This is your actual input. This is the change. This is the output. And we are trying to imitate a continuous thing in a neural net world. So there are two ways you could go about it. One is try to make that increment in your ABCD matrices. There's like a linear model there, AX plus BU, okay? You want to learn those matrices. That's what you're trying to do. And you could do those increments in your matrices discretized. And you could go from there. Or you could discretize the time. And you could go from there, okay? So if you discretize the time, it looks like an RNN. If you discretize the matrices, it looks like a CNN. But when you write it down as a CNN, the kernel comes out as a huge thing, okay? So this is how you start. This is your second. You keep writing this. And if you write down the equation, which gives you the kth one, it looks like a gigantic thing. And that whole gigantic thing becomes the kernel of your convolutional neural net. Of course, this is impossible to compute with. And there's a lot of tricks in the paper trying to make this more computationally feasible. You keep approximating to this kernel with a lot of easier things to compute, okay? And when you do that, it looks like a convolutional neural net. If you do the discretization, it looks like an RNN. Usually they train using the tricks. They train like a convolutional neural net. Then when you ask for inference to guess, then it starts behaving like a recurrent neural net. That's the main trick. Training recurrent neural nets is super expensive, but inferring is not necessarily that expensive. You're just trying to literally guess the next word or next token. So that's the main idea behind this thing. It says, let's train like very clever tricks on this kernel, like train like a CNN, infer like an RNN. That's more or less the idea. But there's so many details going into this. It will be, I think if I would try, it would take more than a lecture, so I will not do that. Even in one lecture, I don't know if I can explain you all the math behind. But I will give the reference on Canvas. It's super nice, and I'm happy to discuss with anyone offline. For now, I hope you're just aware that this thing exists. That's the main idea. The rest is up to you to learn or not. I'm happy to help. Okay. All right. And we are almost on time. I have like a minute.